integral formula.
Yes.
Cauchy's integral theorem is actually something else.
Oh.
There are a lot of things named after Cauchy in complex analysis. Cauchy's integral theorem says that I don't want to misstate the usual version of it. Just a second. I'm going to look it up in my guide the game on here. Cauchy's theorem, section 4.3. So I say let D be a bounded domain, piecewise smooth boundary. If f of z is holomorphic and continuously differentiable on D and extends continuously to the boundary of D, then the integral of f of z dz around the boundary is 0. So basically, Cauchy's integral theorem says that if you've got some space, it's nice enough, all right, it's bound, it's like a finite space, it's closed and bounded, and if you have f prime exists in here, then the integral of f of z dz over the boundary is equal to 0. This is Cauchy's integral theorem. It is a more simple theorem than the ones I shared with you earlier. It's a precursor to those, in fact. Like if you look at Cauchy's integral formula, or the residue theorem is better. It's like the residue theorem, residue is 0. If the derivative exists everywhere inside, there's no singularity, the residue is 0. There is no residue, so this is like, the residue theorem collapses back to this in that context for what it's worth. But yeah, this is Cauchy's theorem, which is just a hop, a skip, and a jump from Green's theorem, if you set aside some technical issues about the continuity of the derivative. But anyway, getting back to where we were, corollary 10.11 says that if we have a simply connected subset of an algebra, then the integral around all loops is 0 in U, if and only if f is a-differentiable on U. So, oh, did I miss an if and only if in the other thing? Curses.
Wait. Doesn't this go against the theorem that if big F prime of zeta equal to little f of zeta for all zeta, no, for zeta in CP into Q? The fundamental theory.
Well, it's saying if, I mean, it's a little bit surprising. It's saying if f is a-differentiable, then the integral around the loops are 0.
I thought we got that from the other theorem, though. Yeah. One second. Yeah, why don't we get that from theorem 10.9? Say the same thing.
Half of it's the same.
Mm.
I mean, I think that theorem 10.9 is like one direction of this corollary. That's the proof here, right? It's like, so observe that the integral around all loops and all loop integrals vanishing is equivalent to the existence of an f such that df d zeta is equal to little f, right?
Mm-hmm.
But then that also essentially means that df is equal to f star d zeta, right?
Mm-hmm.
Which is exact on u. Consequently, by the thing we just went through, f is a differentiable. So that's assuming the loops are zero, we'll get a differentiable. So it's a combination of the earlier loop theorem and this thing we just went through.
Okay.
But then the reverse direction, if f is a differentiable, theorem 10.10. That's what we just went through, wasn't it? Oh, that's if and only if. It's an if and only if. Okay, so. Okay, so here, if f is a differentiable, all right, then f star d zeta is exact, which means that f star d zeta is equal to df, but the integral of df around a loop is zero.
Yeah.
So that's the other direction. That's why I don't have it written out, even though I probably should. So I was pleased to find this because while I don't get Cauchys integral formula, I do at least get Cauchys integral theorem, which is just, it's not as powerful a result, but it's a step on the journey. But I already know that I can't get to the integral formula for the reasons I told you before, like the existence of these once but not many times differentiable formula functions over the rails. Oh, there's more. Theorem 10.12. I say if we have a curve from zeta naught to zeta, and U is an open, simply connected subset of A, and if f is a differentiable on U, then the derivative of the integral of f of eta d eta is f of zeta. So essentially the argument is just, since f is differentiable, it implies that f of eta star d eta is integrates to zero around loops, which means it's path independent, which means that our construction of the potential works, which means that the derivative with respect to zeta of the integral, the curve C goes from zeta naught to zeta. It's that,
yeah,
it's that thing again. So it's, anyway, this is the analog of FTC1. Yeah.
Is 10.13 just a example 12, which is like essentially this, just on a different sense?
What is example 10.13? It is a commutative unit of algebra which meaningfully write integral from 1 to zeta d eta over eta. Yes, this is actually this is how we can define the logarithm near the identity. Near the identity.
As the integral of 1 over n, essentially.
Yeah. And that 7 is, I think that's Bedell's paper. Oh no, that's Freeze. That's the next one we're looking at. Need a drink?
Oh.
So, one possible direction for work, something that comes up in other questions later, especially when you use integration, is like, okay, so Koshis integral formula is not true in general, but it's sometimes true for the A calculus because A could be C. And then a sort of fuzzy question I've had for a while is like, what if there's some isomorphic copy of C inside your algebra? You know?
Like it's like C's in there, just like not as big. Like if you like restricted an algebra to C.
Something like I don't know quite what I mean by that.
Okay.
But that's part of the fuzziness. And is there a meaningful way that you could find subsets of the algebra and curves in the algebra for which the Cauchys integral formula still came together for those subsets, you know?
Yeah, in the hyperbolic sense, I find problems already because we transcribe C to E to the pi I, and there's a real but like with the real component of it, there's going to be discontinuity somewhere with that theorem that it's always differentiable.
Yeah. We've looked at integrals over the hyperbolic numbers a fair amount. I spent a while trying to do those in one of those courses I linked to you.
Mm-hmm.
I never came to a satisfactory understanding of them. The way you have to deal with the zero divisors, like, I didn't get to a place where I understood what was going on yet. And if I try to do something like integrate, like suppose I want to integrate around a circle, like what do? How do I deal with the zero divisors? Well, we tried various things. Like we tried approaching the zero divisors like symmetrically from both sides, kind of like a principal value. But again, I never could quite convince myself of what was going on. But I want to believe in something like H3, where you do have an isomorphism of that to the complex numbers, direct product with the reals. Maybe there's hope for there being more of the complex theory surviving on that complex component. But that's just a fuzzy hope. Like, so that if I could find more examples of that, I'd be happy. But I probably should do what would be wiser is if I'd start by looking more at how does calculus work on the direct product algebra. Just do that first, rather than trying. H3 is hard. Instead, see what I can say about C cross R to start with. Just like, can I meaningfully implement Cauchys integral theorem there? So that's a possible direction we could look at. Yeah. So, shall we move on to the next paper, or do you want to take a break?
I'm just thinking of like questions to like work on, like because I have like a week. Well, I'm gonna stay. I have to stay at least till tomorrow.
It is.
Louis in some pain, but it's okay. I just need something like to work on. That like I kind of want it to like apply to something that like we've been working on as well, like a question, or at least leading into something.
Mm-hmm. But that's pretty much what I have of integral calculus. I haven't tried really hard to prove or disprove. I mean, like, I know certain theorems of complex analysis can't be generally true, but like, can I weaken the hypothesis for them to be true across a wide class of algebra? There's all kinds of things like that. Probably could.
So how do algebra get affected when you start adding another variable, like more variables?
What do you mean?
You know, because we've been working with just like certain things like x plus iy, x plus jy. What happens if you have like xj plus jy, like or xi plus jy?
Well, then you have to. I don't think it's really much different. I mean, we saw the quaternions.
Mm-hmm.
There you have the I, J, and K. Trying to remember. I think you can work with. Let me see about this one. A equal to A plus BI plus CJ plus DIJ. I think we can work with that such that I squared is -1 and J squared is 1. And IJ equals to JI. I think that's a thing. You gotta be careful. You know, it does have to be associative. It does have to. I mean, I've gotten myself very confused in the past by just writing something down and going, oh, okay, well, and then, oh, no, it doesn't satisfy theorem, and then like take a deeper look at it and go, oh, wait a minute, that's not even an algebra, so it's not a counterexample. So you got to be wary of when you adjust an example by like just a little bit. Have you actually jumped the shark in terms of like context, you know? But here my feeling, and we proceed normally, right? Like, I think this is a thing. And I think in terms of abstract algebra, you could generate this sort of thing by looking at something like polynomials in 2 variables, and then like quotient by, you know, well, you want like x squared plus 1 and y squared minus 1. Something like that, I think, would be what this is. And the working in polynomials, xy, it automatically has xy equal to yx. So like, I think that's already there. I'm a little fuzzy on this, but anyway, I think this is a thing. And you could.
Hello.
Oh no.
I am back. I'm back from the party. It was very, very much fun.
Expected this.
It was so
So
fun.
we can work out the regular representation, you know. That might be instructive, I don't know. So if I have A plus BI plus CJ plus D I times J, and we multiply that by, you know, X plus Y I plus ZJ plus WIJ, right?
Mm-hmm.
That would give us AX, B times I squared is -1, so minus BY, plus CZ, J squared is 1. What's IJ squared?
-1.
So, assuming they can get right squared, I think you're right, -1. So
No,
it's,
I think it's 1. No, yeah, it's 1. J's 1, I squared should be 1.
but it's
Yeah. No.
You were right, it's -1. So this is minus dw, right?
Mm-hmm.
And then plus I times bx plus ay. All right. let's see here, CW. C because J times IJ. And D DZ plus DZ, right? Plus J times I don't know, AZ plus
BW.
I was gonna say CX, but EB. What was it? What do you got?
BW minus BW.
Oh yeah, minus BW, please.
CJ, CX, yeah, I already got that. No, that would give me an I.
Oh yeah.
Already, no. Well, that'd give me an I too.
Oh, so minus BY, right?
Yeah.
I should just pay more attention to the letters that aren't there, you know?
Yeah. And then we need IJ.
Uh-huh.
That should be B and Z. And then C and Y.
So we get, yeah, I'm gonna be like AW plus, what do you say, B, DZ, C what?
CY, DX.
Alright, so whatever I put here will be the regular representation.
So A plus IB. Oh, I'm going. Yeah, IB.
Oh, so A, let me see, minus B?
Wait, no, it should be. I'm going. I'm
That's
sorry.
the-
I'm going down. Like, I'm
No,
going
yeah.
by column.
Gotta go component by component. This is the real component, which goes the first row.
Minus B plus C,
Mhm.
W minus D, B, C, D all plus 2D.
Oh, D.
Yeah, D, W, and C, yeah. And then C, minus D, B, minus B, and then D, C, B. Okay, that looks good.
I'll give you something. Like, I'll give you a legendary skill. Oh no, I won't. I'll do my best. Honestly. And these two are like total moves. What if I rigged it? Yeah, bunker guns is usually here. Like at rainbow round.
Kind of neat pattern, right?
Yeah, that's what I thought too.
And so I think if we go back to our original form, we got A plus BI, right? Plus J times C plus DI.
Yeah.
That corresponds to the fact here that we have, oh, I can't remember. I never can remember the stupid tensor. What was, did I write? wish I could, for the life of me, I wish I could just remember the tensor product, like the way it goes. Always forget this line.
Absolutely no way.
Don't be like me.
That's a big ask. So not to remember things off the top of your head all the time. I don't even think people with eidetic memories can do that.
Let's see here. Alright, so what we have is the 1, 0, 0, 1 matrix tensored with A minus B, BA, plus the 0, 1, 1, 0 matrix tensored with the C minus D, D, C matrix. Not an accident. This is the matrix representation in the, of course, the hyperbolics of number 1. This is the matrix representation in the hyperbolics of J. This is the matrix representation in the complex numbers of A plus BI. And this is the matrix representation in the complex numbers of C plus DI.
Why do we get the identity in one and not in the other? Like the 2 by 2 identity.
I think it's because we did
You pulled the J out.
we pulled the J out. So probably you could also write this, or you could write this A plus CJ
I
plus I times B,
plus DJ.
so yeah, plus DJ.
And that would flip the matrices.
Yeah, but I would suspect, my suspicion is that if we use the basis 1J IJ,
It would do that naturally.
then you'll get you'll get the regular representation having the form I tensor ACCA plus so minus the imaginary number is represented by this. So this So I think that is literally just, well, it's two things. You gotta flip, you gotta like flip these and also flip those. So like flip, alright. So the first flip gets the C to the minus B and the B to the C, right? And then the next flip again flips this to this and this to this, and then it, I think you can almost see this from that
Yeah.
in terms of switching row 2 and 3 and also then column 2 and 3. I don't know if this answers your question or not, but here's an example with two generators. Now, you could ask, is it possible to write this in terms of one generator? I have no earthly idea.
you'd have to get something that squares. Oh no.
Yeah, I don't know.
No, there's no way. Like I was gonna think, I was like, well maybe it's something like every time you square it, it changes the sign, but I was like, that's just I.
Yeah.
You square I, it gives you -1, and fourth it gives you +1, and so on and so forth.
Yeah, I just don't know, but,
I mean, yeah, 1 isn't one of those numbers you can finesse.
So the next paper that I wrote with Daniel Fries is about calculus 2. So what do you study calculus 2?
Mm-hmm.
Basically sequences and series, right? And power series. Right?
Yeah.
And so we look at all those things. And so what's a sequence in an algebra? You know? So A sub n from like the natural numbers to the algebra is a sequence. It's all just a function from natural numbers to the algebra. And here's the really interesting limit, as n goes to infinity, of a sub n equals to L, right, if and only if what? For each epsilon greater than 0, there exists a big N on the natural numbers, such that what? Such that n greater than, and so for the purposes of this paper, since we're working so much with little n being an index of a sequence, I start to use a big N for the dimension of the algebra in this paper. Just to have, if I recall correctly, because sometimes I just want to use little n for the index of the sequence and not for the dimension of the algebra, so that's my out. That's my way around it. Now, one of the things you should find if you read this paper is that it has like a super fast, condensed summary of what we just talked about in the first paper. Like the first about 10 pages of it are just the 50-page paper I just went through with you, condensed down as like, 10 pages. So it's pretty cool. I think it's helpful to you as you're learning to have it rewritten in a more compact fashion, just to kind of review at this point. Anyway, so the definition is for each epsilon greater than 0, there exists an n and n such that for n little n greater than big N, oh, unfortunate. You don't mind? I'm just going to ignore this issue. Okay?
Okay.
So don't assume that this is the dimension of the algebra here is all I'm saying, okay? N greater than that implies what? The norm, a sub n minus L, is less than epsilon. So that should have been how you define convergence of a sequence in Calc 2, right? Which is just a fancy way of saying that you can go far enough out to get as close as you want to the limiting value, right?
Yeah.
And so once you have sequences, what can you do? You can add them, you can subtract them, right? You can multiply them by an algebra number, right? You can multiply them. I'll just stick with that. Those are two. I guess if your one sequence was completely devoid of zero divisors, you could multiply by the multiplicative inverse, right? Those are 4 ways to create new sequences from old. And shockingly, we prove that if AN and BN converge to, let's say, L sub A and L sub B's respectively, guess what? This converges to L sub A plus or minus L sub B. This converges to C star L sub A. This converges to L sub A star L sub B. And this converges to L sub A star L sub B inverse. Of course, assuming that it's an invertible element, right? As n goes to infinity. So, to summarize, what Daniel and I found about sequences, they work. And it's boring. I mean, well, boring is, it's just nothing surprising. I mean, everything surprising about sequences for us was experienced in what it took to prove these statements. All right?
Yeah.
So, like, the proof of these things, you can see on my, this paper I'm starting to talk to you about here. I'll tell you what it is in a second. The theory of series in the A calculus and the N Pythagorean theorem. Again, this is work with Daniel Fries.
Who is he, by the way?
Oh, he was a student that I had, theory of series. This is linked on my webpage, of course.
Yeah. Well, I have it here. I have it pulled up.
But I taught Daniel. I'm trying to remember. I think he had a work study to do research with me in like fall 15.
Mm-hmm.
And then we did a lot of it there. And then he was busy, so he couldn't come back to it right away. So we kind of finished it up over like spring 16, I want to say. And then I worked with Vidal in the summer of 16. I think it was. Clean things up further there. So Nathan and Daniel worked some together, but anyway, he's at Indiana now. He studies differential geometry. As far as I know, he's at Indiana. Actually, I don't know for sure. Let's see here. So yeah, the theorem I'm mentioning right here is theorem 3.4 on page 9. And, well, there is one interesting aspect, which is that these are vector value sequences, right? So like, so A sub n is actually, AN1, AN2, AN, see now we're getting in trouble. Let's say big N. That is the algebra dimension. My point is there's components, and like one of the theorems says that the limit as, n goes to infinity, let me use a J, just to get away from my N issues here. So the limit as J goes to infinity of A sub J is equal to L, which by the way is L1, L2, L big N. That's true for only the limit as J goes to infinity of A sub J I is equal to L sub L over I for all I. So what this says is that a sequence of, vectors converges to the limiting vector if and only if each one of the component sequence likewise converges to the same component of that limiting vector. This is not really an A calculus thing. This is something that's known from study of sequences and vector spaces. But anyway, if you look at pages 9 with me,
Yeah.
like under theorem 3.4,
Yeah, you state all the things you just. Oh wait, no.
so you can start to appreciate the proofs, you know, they all involve the submultiplicative constant of the algebra
Mm-hmm.
and kind of massaging it around. That is not something that you face in the real calculus, because in like real or complex calculus, you just have multiplicative norm. So you don't have that submultiplicative constant entering in and clouding the issues. So it just complicates all the proofs, but they still happen. The worst in these is, I think, on page 10, the product of two sequences. It gets kind of messy, and you don't really appreciate how messy it is until you get to page 11 and see that in order to make sense of it, we had to deal with like 4 different kinds of terms, and it's just, you should be glad it's been done. Okay. I'm glad it's been done. All right. Now, of course, most people have the good sense to just say, "Oh, it's obvious," and they don't write this stuff out. But there it is. So this theory of sequences works like you'd expect. Continuity of functions. So you haven't had real analysis yet, right?
No, I'm taking on this ball.
So there's a sequential characterization of continuity, and there's the epsilon delta characterization of continuity. So the epsilon delta definition of continuity involves epsilons and deltas. You maybe saw that in Calc 1.
Maybe.
I know we looked at this before. I think this is what Spencer liked this example.
Yeah.
Right.
Oh, you erased all the cool man.
Oh no.
I was going to take a picture for the big bad.
Oh.
Since his mom said he wanted to learn these concepts, just not the calculation.
For each epsilon greater than 0, there exists a delta greater than 0, such that 0 less than norm of x minus x naught less than delta implies the norm of f of x minus f of x naught less than epsilon. Then f is continuous at x equals to x naught. So this is the epsilon delta definition of continuity. And this works for a function whose domain and range, domain and target space are both norm spaces. And in real analysis you might state a similar thing in terms of metrics, but anyway, whatever. That's epsilon delta continuity. It's written in terms of like inequalities involving the norms. Sequential continuity says that if let's see here. For all, let's say for all xn converging to x naught, blah, 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 blah. As n goes to infinity, if for all, that implies that the f of xn goes to f of x naught as n goes to infinity, then f is sequentially continuous. At x naught. So as you can see, these are, quite different looking definitions, right? I mean, one is kind of forward directed, right? Like you just take any sequence in the domain, which is going towards the, x naught, and then track where the corresponding image sequences go. And if they likewise converge, function is continuous. That's sequential continuity. In contrast, this, it's kind of backwards. Like for every epsilon greater than 0, epsilon has to do with the range.
Yeah.
And then you're tracking back and finding a delta such that you can get close enough to the limit point that forces you to be close.
To epsilon.
So I've always felt like this is kind of backwards, whereas this is kind of forward. But they are equivalent. One of the things you should prove in real analysis is that sequential continuity implies that you can go one or the other. This implies this is pretty easy because you can always make like epsilon. You can play games with like 1 over n and such. And I'm not going to get into it. Proving these are equivalent is a rite of passage we should all go through. But theorem 3.5 says that in a calculus, you can characterize continuity of a function either with epsilon delta or the sequential definition. So, we also have that freedom. And here I actually have proof. So,
Oh, yes.
you can study this if you like. Now, example 3.6 is kind of fun. So suppose you got the square function, right? Pick a sequence Cn that goes to Z naught. So then we can look at f of Zn. That's Zn times Zn, right? Which by the product of sequences theorem is the limit of Zn times the limit of Zn. Both exist or Z naught. We get Z naught squared, which is f of Z naught. Consequently, we have shown that the square function is everywhere continuous. Now, probably wouldn't be much trouble to prove that directly by the epsilon delta definition, but sequential arguments are actually very, sequential. Now, Cauchy sequences. Cauchy means that for every epsilon greater than 0, you can go far enough in the sequence such that the difference between any two things in the sequence is as small as you like. So, in a complete space, Cauchy implies convergent. But in a space like rational numbers, it's not the case. You can have Cauchy sequences of rational numbers which converge to something that's not rational. For example, any truncated decimal expansion of the square root of 2 is a rational number, but the limit of that sequence is the square root of 2, which is not rational. So there you go. That's a Cauchy, and that can be shown to be a Cauchy sequence. But, anyway, then you have this Cauchy criterion. So the Cauchy criterion essentially is that it's convergent if and only if it's Cauchy. So the A numbers work just like real numbers. Real numbers, not like rational numbers. Real numbers, Cauchy implies convergent. And that's often useful because it's easier to check the Cauchy condition than it is to check directly convergence of a sequence. Like manipulating differences of a sequence is sometimes more productive than actually just looking at an arbitrary element of the sequence. It's a big convenience in analysis. And we also have that convenience in A calculus.
And then, can you rewrite like the equations using these sequences since they work the same? Like, have you guys like you know like put the Taylor series in like another algebra? Like, if that makes any sense?
What can we do with this stuff?
Yeah, like can you like rewrite Taylor series and?
Oh yes, we'll get there, we'll get there.
Oh, okay.
So let's skip ahead a bit here. So basically, I plot along here and prove things about sequences, right? Oh, we're actually at the end of it. Now next series.
Mm-hmm.
All right. So remember what you know about series? In calculus 2, you've got geometric series, you got p-series, you got integral test, you got the ratio test, you got direct comparison, you got limit comparison, you got your root test. That's about it. Do you remember what the domain of power series looks like?
Is that the like the 1 plus x squared plus x2?
Oh, remember we have to like find the interval of convergence for power series for a series. Power series, like typical Calc 2 question. Find the integral of convergence for this power series.
Like find the integral from the series, like find what it's integrating.
Interval of convergence. So, for example, some x to the k.
Mm-hmm.
K equals 0 to infinity. This is a power series, right? So it's 1 plus x squared.
Yeah. Like are you talking like what's the interval between each term?
No, for what's the domain? If this is f of x, what's the domain of that? That's the interval of convergence.
The domain of f, I would say it's just a positive infinity integral. No?
So you can I guess what I would do here is I'd say, well, that's 1 over minus x, provided that the norm of x is less than 1.
Mm-hmm.
Absolute value of x is less than 1. So this is the geometric series result. So this shows you that minus 1 to 1 is a subset of the domain of f. However, actually the geometric series not only says that this converges given that condition, it also, part of the theorem, geometric series, is that if the absolute value of x is greater than or equal to 1, then you get divergence. So because of that, I can actually say this is too weak. I can actually say that the domain of this function is in fact minus 1 to 1. This is the so-called IOC, interval of convergence for the series. The radius of convergence.
Why is the absolute value of x less than 1?
Well, thank you.
Oh, geometric series.
From 2 years ago. Because like the last thing is no, that shouldn't be equal to 1. Or am I going crazy?
Well, oh, okay. Let me take a step back here. Okay, so if we have, if our nth Sn is a plus ar plus ar squared, ar to the n, let's say,
Yeah.
then r times Sn is ar plus ar squared, ar to the n plus 1.
Mm-hmm.
Right? So S minus Rsn minus Rsn is, these cancel.
Yeah, you just get a.
A minus and net.
Yeah.
Therefore, Sn is a minus ar to the n plus 1 divided by minus r. So, the limit as n goes to infinity of Sn is the limit as n goes to infinity of, I can factor the a out, right?
Yeah. Where'd you get the 1 minus r from?
Factoring.
Oh, okay.
So this is the geometric series, and it is a precious and wonderful example because it is one of the precious few examples where we can straight calculate the formula for the nth partial sum. That is a formula, some full formula for the nth partial sum. Actually, it's the n plus 1, whatever. And then so I can calculate the limit as n goes to infinity. If that exists, the series converges. If it doesn't, it diverges.
Yeah.
When can this exist? Well,
Less than 1.
yeah, we need that the absolute value of r is less than 1 in order for this term
Yeah. To keep going.
to
Or,
go to 0.
yeah.
And so if that's the case, then this is equal to a over 1 minus r. And it does not exist, it's divergent if the absolute value of r is greater than or equal to 1. Because then this either blows up to infinity or goes to something that oscillates between plus and minus infinity like math.
Okay, and so coming back over to this, we get that, so domain has to be between -1 and 1. Yeah, okay, thank you now.
So my point to you is that there's this terminology, interval of convergence, radius of convergence. That is logical because the domain for a power series, right? If you have f of x is defined by some k equals 0 to infinity, like a sub k, x minus x naught to the power k. In other words, this means this is what's called a power series centered at x naught, right? Then the domain of this function is symmetric about x naught. In fact, the domain is an interval. That means there are 10 possibilities. The 10 possibilities? The one... I sometimes forget about this case, but the IOC,
Mom, can I have the crumbs in
it
this?
could be just the set containing x naught itself. Or, yeah.
Does that give you 0?
Yeah, and so like it might be that's the only place where this series is identical to 0. So for example, what could make that happen is if you had like a sub k equal to like k factorial,
Okay.
something like that.
Mama, am I able to have a store? After supper? Because I haven't had s'mores
Don't think
yet
it'd be-
today.
It'd be something like something characterized by the x value of x minus x naught less than or equal to r. Something like that. All x that satisfies that kind of condition. Now there's 4 different cases that can come up in there. These are the finite cases. You could have x naught minus r, x naught plus r. You could have x naught minus r included. X naught plus r not included. You could have them both included. And, oh, you can also have this one. So the question is, do you exclude or include the right and left endpoints?
Is that one supposed to have a bracket on the right side?
Yeah, they're supposed to be bracket. This is supposed to be bracket. And
That's a bracket.
yeah.
Yeah.
So these are the rate. So r equals to 0, r less than infinity, and then the other case is. Oh, I was wrong. There aren't 10 cases. Really, there are just. Five, 6. The other case is that r is infinity. In which case the IOC is minus infinity to infinity, right? Actually, there's other kinds of intervals which don't appear here, like